animal here with reduced weight bearing on one of those limbs. Economic losses are also associated with lameness in swine, so possible increase of treatment costs, and also lameness in swine being one of the #1 reasons of culling breeding stock. So as I mentioned, lameness in swine, there are different causes, and we're going to break it down into non-infectious and infectious causes. Non-infectious, so not limited to, but here are some examples, being management, housing, trauma, genetic selection, and also infectious causes being viral or bacterial. And today specifically, we'll be looking at a bacterial agent that can cause lameness in growing pigs. So that case or that example, that group of producers that were experiencing that lameness in their growing and finishing sites were due to Mycoplasma hyosynoviae. So there was vet reports, different diagnostics that were conducted to ultimately diagnose for Mycoplasma hyosynoviae. So Mycoplasma hyosynoviae is a commensal bacterium, meaning that we can detect it almost everywhere. However, it may not necessarily be causing that lameness. It has been proven, though, to be pathogenic and cause that lameness. There's been a systemic spread that has been suggested, so it's been found to be colonizing in the tonsils and then systemically move through the body to those joints. And then more on a herd level, sows have been considered to be one of the main reservoirs for this bacterium. However, pen-to-pen contact has been investigated through lateral transmission and experimental models by Hagedorn Olsen and others in 1999, and they have also found success of seeing that lateral transmission between pigs. So this is a timeline of Mycoplasma hyosynoviae associated lameness. This is age in weeks represented on this timeline. So at birth, we're not seeing any Mycoplasma hyosynoviae lameness, and you're really not seeing it until as early as 8 to 10 weeks of age. And then throughout that duration of that line, we can see lameness become onset anytime throughout there. And we also see that arrow continue past 24 weeks of age because it can be prevalent in breeding stock as well. So an increase in prevalence has been suggested in recent years, or more so an increase in detection of this bacterium. So a retrospective analysis done by Iowa State Group in 2019 saw that VDL cases submitted approximately 20% of that total lame cases were due to Mycoplasma hyosynoviae. However, diagnostic interpretations can often be difficult to interpret. We'll talk about that more. But this is an example by Pillman and others in 2019 of field data. So we have our CT values on our y-axis and then age in weeks on our x-axis. If I can go back, there we go. And we see at around 5 weeks of age, you're not detecting that bacterium because, again, late colonization of this bacterium, but moving into the age in weeks of around 10 weeks of age and then persisting through finishing age, really being able to detect Mycoplasma hyosynoviae in this scenario. So clinical signs, like I mentioned, onset lameness as early as 8 to 10 weeks and then can persist through that duration of the animal's life. Ross and Duncan in 1970 looked at maybe that persistence of that mean length of lameness, and they found approximately 3 to 10 days of that persistence of lameness. However, they do stress that it can occur longer as well. Joint tropism has been investigated. However, there has been no specific joints that have really alluded to being prevalent for Mycoplasma hyosynoviae, especially because several joints may be affected at the same time. And this also goes into the complexity of diagnosing as well. And then lesions can vary depending on state of infection. So acute lesions we're going to see looking different than chronic lesions. This is an example of a chronic lesion from our field data. So this is a stifle joint affected by Mycoplasma hyosynoviae. And this joint fluid here with this arrow, there was excessive joint fluid, but we're looking at a really dark color of that joint fluid in that stifle joint. And then also thickens tissue in these two areas from that cell proliferation really trying to fight off that bacterial infection. So how do we manage Mycoplasma hyosynoviae? There's different options here listed. Management is one. However, there hasn't been any direct investigations looking at being directly associated with Mycoplasma hyosynoviae. So we know that management can improve certain lameness in swine, so that would be a great next step of looking into how can we improve this through management. Treatment is another option. So arguably the most common option for Mycoplasma hyosynoviae is treatment through antimicrobials. However, these unfortunately vary in successfulness. And then immunity, inducing a humoral immune response may be another option. So maternal antibody protection has been investigated. Lauritsen and others in 2017 indicated and suggested that there was passive immunity that protected those piglets later in life against lameness. However, Macedo and others in 2019 saw contradicting results. Currently, to date, there are no commercial vaccines available. However, we do have the other option of utilizing an autogenous vaccine. So with all those different options, what intervention do we use and when should we apply it? So as I said, management, however, there isn't no direct correlation with Mycoplasma hyosynoviae, but this is something that we could manage and account for throughout that whole duration of that animal's life. Antibiotics, you don't want to be applying antibiotics this whole timeline, but there are different spaces of when we could apply that treatment. However, the question is, do we apply it before the onset of lameness? Is that going to provide treatment, or are we going to miss that opportunity? Maternal antibodies, so following birth and those colostrum receiving that passive immunity from those dams. However, we see that is a few weeks and months that we're not going to be able to maybe protect them from later in life. And then a vaccine is being another option of we could induce this immunity response. However, when should we apply it? So this is some data I presented last year at the Leman conference, and this is natural Mycoplasma hyosynoviae IgG antibodies in a clinically affected herd. So there are SP values on our y-axis, and then our x-axis had different time points that we sampled. And that lighter blue color is going to be our piglets. And we see that antibodies were really high in life and really tended to wane around 7 to 10 weeks of age. So kind of using that information, maybe we should apply this vaccine later in life. So with those objectives, or with those questions in mind, we led us to our objectives of investigating the production, clinical, and diagnostic outcomes following vaccination against Mycoplasma hyosynoviae, and with that, is there an optimal time to apply that vaccine? So we enrolled approximately a 9,000 head sow farm that was clinically affected with Mycoplasma hyosynoviae, a farrow-to-wean operation, and then also 11 different downstream sites were enrolled. And this was strictly just based on the production schedule of their enrollment. And then during the case of this investigation, antimicrobial usage was limited. So as a majority at a herd level, we did not apply any antibiotics that would have affected Mycoplasma hyosynoviae, but individual basis for welfare, we made sure that if a pig was extremely lame, that we were going to record that usage as well. So enrollment, over 12,000 dams were randomly allocated into either non-vaccinated or vaccinated treatment groups. Even distribution from parities was also involved in the enrollment process, and this was just strictly based on the parity structure of that farm. And then over 12,000 of those piglets were also going to be randomly enrolled into the project, and their treatment group is dependent on their dam vaccination status. So a different illustration to look at it is that random allocation into treatment groups A through D were from those non-vaccinated dams. And then on the other side, if you were randomly enrolled into treatment groups E through H, your mother was a vaccinated dam. So within 24 hours post-farrowing, all the piglets in the litter were numbered, and then utilizing a randomization software were randomly enrolled in multiples of 4, being 4, 8, and a maximum of 12 piglets enrolled into the trial. And then during that enrollment process, our randomization of our treatments were also included. So at enrollment, individual birth weight was recorded, they were individually ear tagged, sex was recorded, sow ID, they were ear notched for a second identification, and then also again recording that treatment group that they were allocated into. So I was not exaggerating, it really was over 12,000 piglets. However, we needed that large sample size to detect those differences because we're going off of a very low prevalence estimate of approximately 5%. And this was from a study of Pillman and others in 2019. And also being in commercial conditions, we want to make sure we're really on that lower end of that estimation, so again, going with that 5%. And having more than a few treatment groups, so 8 in total, really increases that sample size as well. So looking at our treatment groups, so we have treatment groups A through H, and as I mentioned, treatment groups A through D are going to be born to those non-vaccinated sows, and treatment groups E through H are born to vaccinated sows. So A is our strictly controlled group. They did not receive any vaccination, and they're born to non-vaccinated sows. Treatment groups B through D, born to non-vaccinated sows, however, they're going to start those piglet vaccinations. So treatment group B, they were vaccinated twice in lactation. Treatment group C received one of their doses in lactation, once in nursery, and then treatment group D being vaccinated twice in the nursery setting. And then treatment groups E through H is going to be a mere replicate of that. The only difference is that these are going to be born to vaccinated dams. So the vaccine that we utilized was a autogenous bacterin that was formulated and manufactured by Vaccinova, and it was 2 doses of 1 ml administered intramuscularly with 2-week intervals. So this is an overwhelming graph, but this is our experimental design. So this is our layout with our vaccines, our vaccinations, and then we also have our outcomes that we're going to be investigating. So starting with that sow and gilt vaccination at 5 and 3 weeks prior to farrowing. And then at farrowing, we have all of our piglets being enrolled. They were all individually weighed. Then we also started serum samples in the subset as well. In processing, we're starting some of those vaccinations in those early groups. Weaning, we're taking more individual weights, more diagnostics through tonsillar swabs and serum samples, and then moving into nursery and growing phase, wrapping up those vaccinations, and then also collecting another subset of weights, another subset of diagnostics, and starting lameness scoring. So lameness scoring occurred weekly and then persisted until approximately 24 weeks of age in the finishing. And then at finishing, we again took more subsets of diagnostics and also did another subsets of weights. And then we also did one final count of all of our live and ear-tagged pigs at the end of the trial. So our outcomes broken down into more broad categories are going to be production, clinical, and diagnostic. So production, today specifically, we're only be looking at our finishing weights because this was the only time that those pigs had had a chance to all receive that treatment. At growing, some of those were still wrapping up treatments or vaccinations, so that's why we're only going to be looking at finishing weights today. And then clinical was evaluated through lameness scoring, which occurred weekly. And then diagnostics, so detection of the bacterium, we utilized PCR and tonsillar swabs. And then detection of Mycoplasma, hyosynoviae, IgG antibodies, utilizing an ELISA in serum samples. So our weights, we collected individual birth weights at weaning, and then a subset of over 2,900 at growing and over 2,100 at finishing. So growing was approximately 10 to 14 weeks of age, and then finishing was approximately 20 to 24 weeks of age. We do see, yes, there is some pre-weaning mortality. I'm not giving specific numbers. However, something to keep in mind is we did enroll these piglets within 24 hours of life. So that really increased our pre-weaning mortality as well. And then growing, looking at our 2,900 weights, but specifically today, we're only be looking at our 2,100 finishing weights. And then at enrollment, all of our piglets were individually ear tagged with an ultra-high frequency RFID ear tag, which was a part of a different system. So this system utilized Bluetooth technology, and I'd love to discuss more, but due to the sake of time, we can chat after, but this really ultimately led us to be able to collect these individual weights on such a large scale. So our lameness scoring, so this occurred individually, weekly, starting at approximately 8 weeks of age up till approximately 23, 24 weeks of age. It was a specific numerical scoring method for Mycoplasma hyosynoviae. I was the individual conducting scores, so I was not blinded to the treatment groups. However, it was consistent that I was the same individual doing that. And then scoring took place during different times of day, so I don't show this data, but for example, if I were going to go to site 1 in the morning, the next week I would make sure to go in the afternoon or evening. And this was just to account for different management and shoring times. So this is an adapted version of our scoring method by Nielsen and others in 2001. So it's a numerical scoring from 0 to 4. So 0 is going to be a very healthy pig. They're freely moving in the pen, no reluctance to rise or move. And then moving into 1, there's a little bit of unevenness, maybe some stiffness is observed, and possible reluctant movement. Score 2 is going to be more of that soreness and short steps, possible reduced weight also on a limb. And then score 3, definitely pain is being visualized, 3 limbs only or less. And then score 4 being the most severe with a lot of vocalization of pain and only rows 1 forced. So detection of Mycoplasma hyosynoviae, we utilized tonsillar swabs and tested via real-time PCR for hyosynoviae genetic material. These were submitted to the University of Minnesota VDL, and it was a total of 696, but we have it broken down into our different subsets, so being weaning, growing, and finishing. And then similar, our detection of Mycoplasma hyosynoviae IgG antibodies through sera samples, utilizing an indirect ELISA assay specific for Mycoplasma hyosynoviae from Gimenez-L'Oreal in 2019. And then again, similarly, having those subsets of newborns, weaning, growing, and finishing for a total of 829 samples. So the data analyses that we used, so for LATES, we ran a linear mixed regression model looking at specifically those finishing weights and then finishing average daily gain. And then our predictors, we wanted to see, did sow vaccination status or piglet vaccination affect that outcome? And then in that model as well, we adjusted for litter effect based on sow ID and also the age at weighing because there was a little variability with ages. For our lameness outcome, we utilized a mixed effect logistic regression model. So we ended up grouping all of our lame pigs that had received a score 1 through 4 as lame, and then non-lame pigs were going to be those live ear-tagged pigs at the end of the trial. And then same scenario where we're looking at those sow vaccination status and or piglet vaccination status affecting that outcome. And then again, sow identification for that litter effect in the model as well. And then diagnostics, they're analyzed more descriptively, so we're looking at the proportions of positive and negative CT values. We utilize a Pearson chi-square to test for each treatment group, and then we utilize a Kruskal-Wallis to look at the different mean of the SP values in our IgG antibodies. And then based on any significant outcomes, we ran a Dunn's test for that post hoc analysis as well. All of these analyses were ran in RStudio and R. So moving into our results, again, kind of breaking them down into broad categories. So first, looking at our production outcomes of individual weights at finishing. This is our finishing weight by treatment group. So we have our weight in kilograms on the y-axis, and then also our treatment groups on that x-axis. Just a reminder that piglets in A through D were born to non-vaccinated sows. E through H are going to be born to vaccinated sows. And here we see no statistical difference and not a lot of variability between any of the treatment groups. Similarly, we see that with our average daily gain. So yes, outliers in both of the graphs and both of our finishing weight outcomes. However, that is definitely expected in these commercial conditions. But again, no statistical differences between any of our treatment groups. So then moving into our clinical outcome of that lameness scoring, which occurred weekly. This is our lameness outcome grouped by piglet vaccination. So the piglet vaccination group is going to be grouped specifically on their vaccination timing, and then sow vaccination is its own variable. So ultimately, the sow vaccination status did not show any significant outcomes based on lameness. However, there are differences based on our vaccination status. So if you were to group all of our vaccinated piglets, they're statistically different than our control group. So we see lower odds in all of our vaccinated groups. However, there's going to be no statistical differences between our different vaccination timings. And our probability, so our chance of maybe those pigs developing that lameness downstream looks high in this scenario. But something to keep in mind is that our denominator could have been affected by those ear tags that were lost at the end of our trial. So detection of a bacterium through PCR in our tonsil swabs. I apologize for the small graph here, but these are CT values on our y-axis, and then our same order of our treatment groups on that x-axis. And then so a CT value of 40 or above is going to be considered negative, and anything below that is going to be considered positive. And that's also being shown in our table here on the right side, and then percentages of positives on the far right. So statistically, we're not going to see any differences because we barely detected hyosynoviae at our weaning stage. But moving into our growing, we see those percentages of positives definitely increase. However, no statistical differences between those treatment groups when comparing them. And then into finishing, we see almost all of our treatment groups, they're well over 50% detectable for hyosynoviae, but again, no differences between those treatment groups. So then moving into our final outcome of detection of antibodies. So this is our similar layout. However, our SP values are going to be represented on that y-axis, same order of our treatment groups on our x-axis, and then our 0.6 line here is going to be our cutoff. So anything below that is considered negative, anything above that is considered positive. And that's also shown here in our table with the similar design of percentages of positives on the far right. So newborns, something to note is that these newborns were sampled post-suckling. So it was approximately 6 to 24 hours of age that we sampled these piglets, so that is something to keep in mind. So numerically, we do see that all piglets born to vaccinated sows numerically had higher detection of these IgG antibodies for detection. And then statistically, looking at those pairwise differences, there is a difference between treatment groups B and F and D and H. So B and F were vaccinated at 1 and 3 weeks of age. D and H were vaccinated at 8 and 10 weeks of age. The only difference is that H and F are going to be born to those vaccinated sows. And then moving into weaning, so we see those percentages of positives definitely decrease a little bit, but still very high detectable for those IgG antibodies. And then similarly, seeing that numerical difference of all those vaccinated sows with their piglets having not a statistical difference of having higher detection, so there was no statistical difference between any of these at weaning specifically. And then moving into our growing, we see those SP values really decrease as a whole across all of our different treatment groups, percentages of positives being represented here. And then statistically, that treatment group B, so vaccinated at 1 and 3 weeks of age, however, we're only going to see a statistical difference in that non-vaccinated group, which was surprising on my end. But only difference being with that control group, which was non-vaccinated, and then treatment group D being vaccinated the latest at 8 and 10 weeks of age. And then moving into finishing, those SP values definitely increase again. Those percentages of positives as a whole increase, but statistically seeing no differences between any of the treatment groups. So in summary, looking at our big buckets of our outcomes again, production, looking at those weights, there were no statistical differences in our finishing weights. And as a disclaimer, looking at sow vaccination, no statistical differences at growing and weaning as well. And then clinical, our outcome, looking at lameness scoring, we do see that all piglets that were vaccinated exhibited those lower odds of lameness. And then diagnostics, we saw equal colonization across all treatment groups with no statistical differences. And then those IgG antibodies, we do see that sow vaccination did have an influence early in life at that newborn and weaning stage. However, it did not carry through in that growing or finishing stage. Some little limitations to mention is that we were not able to track mortality real time just due to the size of the study. I wasn't able to track that weekly, and that may have led into the second bullet point of that mortality or possible fallout of those pigs were not evenly distributed across all of our treatment groups. And then this is one production system being evaluated, so that is something to keep in mind moving forward. So in conclusion, piglets vaccinated against Mycoplasma hyosynoviae, they did exhibit and showed less lameness. However, it was regardless of application timing. So going back to our original scenario of those producers that had been experiencing this lameness before their diagnosis of Mycoplasma hyosynoviae, with our results, it's still very complex to diagnose based on that colonization pattern and those IgG antibodies as well. Decreased animal welfare was a concern, and we do see that was reduced based on vaccination status. And then economic losses, I think this would be a great segue into a future project of maybe making that comparison of different treatment groups or different vaccinations as well. But with that, I want to thank you all for your attention. I want to thank all of the funding agencies and collaborators on this project. It was a massive project, so I had so much help and so many fun memories were made. But I want to give a special shout out to the Sow Farm team and the producers who allowed me willingly into their sites, to PAR research team, Erin Little and her team for all of the physical labor as well. And a big thank you to the U of M Swine graduate students and DVM students that helped on this project. And with that, I would love to answer any questions.
We'll have some microphones in the room if there are any questions. To start with, I'll ask, any opportunity to follow these pigs post-marketing and to the plant to evaluate maybe issues with carcasses?
Yeah, great question. That was an objective we did have in mind, and we really wish we could have went through with that, but based on the size and just the production system schedule, I wasn't able to capture any carcass data.
Great work. I really enjoyed it. Good design and a lot of work based on the number of pigs and things that you measure. Anyway, I was wondering, you show us roughly 5% reduction in your positive or negative for a lame pig, right? Which is great. But I was wondering more on what were the fallouts or the removals that you have based on a lame pig, because several causes of mortality and removals, right? But what were the ones related to lameness that you can see a difference between your treatments, and also what will be the difference in severity, because you have your scale from 0 to 4. Did vaccination affected also that severity?
Yeah, great question. So we do have plans of running like an ordinal regression and looking at that severity because that's the only data we have. Because unfortunately, we don't have that mortality or pullout data. Just due to the size of the project, I wasn't able to obtain all that data and information. So I'm not able to answer the question on what % of that fallout was due to lameness. However, there is, yes, definitely the next step of that data analyses is looking at that different severity of those scores.
I have a question about vaccines. You used an autogenous vaccine, but I'm wondering if people have considered looking at subunit vaccines, and if so, what's the critical antigen that you would target?
Yeah, that's a great question. And unfortunately, there is very limited data around even the use of autogenous vaccines. So I do not know of any of subunit data out there. However, I think that would be a great something to look into.
Maybe a follow-up on that question. So if you are using autogenous vaccine, then on your PCR and the serology, how would you know whether it's due to infection or due to the vaccine?
Yeah, great question. And that's another limitation of this project. I didn't have that up on a bullet point, but that's a great example is that were these naturally exposed or is that from the vaccine? And I think that also is a limitation that all these pigs were from a clinically affected herd, so we're not able to differentiate that. So I think that'd be a great project of utilizing an absolute control group of being non-natural exposure and making sure they're free from hyosynoviae before starting that. Thank you for the questions.
All right. Let's thank Haley again.
Thank you.